You are not taking away to forget your thoughts.
দেখে না বলতাম ও ব্লিঙ্ক করবে না, স্টপ হয়ে যাবে, ওখানে ব্লিঙ্ক করছে, হঠাৎ ব্লিঙ্ক করলো না। এটাও ব্লিঙ্ক করছে, ওটাও ব্লিঙ্ক করছে।
Respected sir, please be seated and let us start our next session. Good afternoon, everyone. Welcome back to the post-lunch session of the third International Conference on Data Mining and Information Security. Data Mining and Data Analytics. Organized by the eminent College of Management and Technology in collaboration with the International Knowledge and Research Foundation. We are excited to continue with the engaging discussions and insightful presentations. To kick off this session, I am pleased to introduce our next distinguished speaker, Dr. Eva Tuba. About Dr. Eva Tuba earned her BA's and MS degrees in Computer Science and Mathematics from the Graduate School of Computer Science at John Nesbitt University and the Faculty of the Mathematics at the University of Belgrade. She later completed her PhD in Computer Science at the Faculty of Informatics and Computing, Singidanam University. Previously, Dr. Tuba has taught Singidanam University's Faculty of Informatics and Computing and Faculty of Technical Sciences. Currently, she serves as an assistant professor at Trinity University, Texas, USA. Her research interests span artificial intelligence, machine learning, swarm intelligence algorithms, image processing, and wireless sensor networks. Dr. Tuba, I am honored. Please come to the dais. For felicitation, I would like to call Dr. Niranjan Dey, Associate Professor at Techno International, Newton, India. Please, be sir. Over to you, Dr. Tuba.
Good afternoon. I hope that after the lunch we are all feeling refreshed and ready to continue with this conference. I want to thank the organizers for inviting me here. It's such a huge honor for me.
May I?
Yes.
Yes,
To be here, and especially not to just be part of this excellent conference, but also to share the stand with excellent speakers that came before me and that will speak after me. I feel very humbled to be in that company. A little bit nervous now among those people to give my thoughts. My talk will be appropriate to my age, not really giving advice like others. I will just go into technical details. So, as you can see, my title is quite similar to Professor Milan Tuba's talk because I'm his rising star, favorite student, favorite child. He doesn't say that often, but it usually is the truth. So we are working in the same area. So I will go into a little bit more technical details of these revolutionary technologies that we have in the past decade. So as he said, we work a lot with digital images because digital images are really in any area. Even before appearance of digital images, we had scientists that are using images. The example is medicine. Medicine is using X-ray, for example, for over a century. And it brought a certain revolution in diagnostic system because now we were able to see inside of human body. We could see broken bones. Then with ultrasound and others, we could see inner organs and find different anomalies. So images in medicine have a huge role. So Digital images, you can say, didn't bring anything new. We had images, now we have images, we still have images. But processing and dealing with digital images is completely different. Digital images are just matrix of numbers, and we can put that into a computer. Computers are really good with numbers and with mathematical operations. So we can process those images really fast, and if we don't like the results, we just go back to the original matrix of numbers, and we have original image, and we can start over. That was not the case with the analog images. So analog images, if you take X-rays, they are sometimes too dark, too light. So we first usage of digital images in medicine, we can enhance images so physician can easily check and find anomalies in those images. So that would be one use. The other use is now when we can process them really fast, we can use digital image processing methods to detect anomalies. So for computer-aided diagnostic systems. Because those digital images are matrix of numbers, by using mathematical formulas, we can sometimes detect things that are not visible to human eye. So computer can see difference in neighboring numbers, but human eye, especially if physician is looking through the images whole day, the lighting is not very good, the image is not very sharp, or many different other conditions can affect the diagnostic. With computer-aided diagnostic systems, we have much more objective analysis of the images. So, as I said, the first use of digital image processing methods would be to enhance image, like in the left image. So from the very dark image, we can get image where we actually see the bones and see what is happening. The second use would be to detect certain things, and it can start for finding where the lungs are, like in these examples, or find where the anomaly in the lungs are, and so on. So this is just an introduction about digital images, and specifically in medicine, how they work through the history and what is happening nowadays when we have digital images and we have all these tools. Another technological development is this virus capsule endoscopy images, where patient would drink a pill that is actually a camera. Camera goes through the digestive tract, and after that, someone needs to analyze that hours-long video and find for bleedings, ulcers, or different anomalies. So this is an example where digital image processing and computer-aided diagnostic is extremely helpful, because instead of having a physicians watching through hours, mostly pointless parts of the video, to find where the anomalies are, we can just use computer-aided diagnostic system that will mark the parts where physicians should look and find what exactly the diagnostic is. Similar stories for MRI images, where a lot of images are produced. So this is about the first part about digital images in the medicine, and now it's what do we do nowadays with those images? So obviously they have a long history in the medicine, but now with these tools, convolutional neural networks, and not just convolutional neural networks, generative adversarial networks, visual transformers, around all these recent buzzwords that you can hear in machine learning, they can be used for digital images. Convolutional neural networks are specifically really good for images. That's why the focus is on them in this talk. So basically, convolutional neural networks just have that initial part where features are extracted automatically. Before, we had to know what the disease, how the disease looks like, what the physician is looking at the image. Is it a lighter shade? Is it a deformed shape? Is it something else? And then we try to find a mathematical equation formula that will actually describe that in the matrix of numbers. Now we just give an image to a convolutional neural network, and we have those several layers that will extract features that do not have specific name and do not have specific meaning to us, but they work good for computer. Computer understand those features, those lines, those points, those different blobs, and combine them together and make very successful prediction. As it was mentioned in the previous talk, with those models, we can get accuracy much higher than for months of the research in the past where we tried to find and extract different features. So this is just to show how convolutional neural networks are actually efficient. So this is the error rate through years on that big ImageNet data set that is used for image classification competition. And in 2012, the error rate dropped for 10%. Before that, it was 1-2% every year. And then every year, the error rate went down with improving convolutional neural networks. So all these, after 2012, those are convolutional neural networks with additional methods. So again, as mentioned in the previous talk, we have the architecture of convolutional neural network is extremely complex. If you take any machine learning model, they have certain hyperparameters that you need to tune and to specifically set for specific problem. In support vector machine, you have the cost function, you have kernel function parameter. In neural networks architecture, how many layers, how many nodes in each layer, is there activation function? All these things need to be set before training can start. So those things that has to be set before training, those are the hyperparameters that we have to set. In convolutional neural networks, we have additional hyperparameters of convolutional and pooling layers. Then we have dropout layers, batch normalization layers, and before training can start, we need to determine that. And the accuracy of the model for specific problem highly depends on the architecture and hyperparameters that we set up front. And that is basically what our research is about, finding that optimal architecture and optimal hyperparameters for specific problem. So this is all about deep learning. So I would just want to make one remark that all this is true if you have good data. So deep learning is not possible if you don't have a data set that is a good labeled data set that you can use. So if you don't have enough samples, you cannot use deep learning. It will be under or overfitted. Also, when you have data sets, you need to be sure that it's balanced, that you have approximately equal amount of images of each class, or you need to do some pre-processing data augmentation where you will try to balance data set. So all this is true with assumptions that we have a good data set. Otherwise, we go to old-fashioned methods and feature extraction and old classifiers. So with assumptions that we have good data set, we are continuing with hyperparameter optimization. So this is just a small list of hyperparameters that we can tune and that we need to set up front in convolutional neural networks. So number of convolutional layers, size and type of kernels or filters. What is the stride padding in each layer? Is there a pooling layer? Is it max or average pooling layer? What is the dropout probability? Epoch number, learning rate, batch size, number, and so on and so on. So one of the naive approaches is just to do the grid search, but this is equivalent to traveling salesman problem. You cannot try all possible combinations. So what we are doing, we are actually adapting swarm intelligence algorithms. So this is the borrowed slide. We are adapting swarm intelligence algorithms for this problem. So swarm intelligence algorithms are really good optimizational algorithms. They're inspired by nature, but all swarm intelligence algorithms, they have few important parts. One is exploration. So when you have optimizational problem, you have a fitness function that you want to minimize or maximize. And you need to have exploration operators. So how do you ensure search of the whole search space to find promising area? Once you find promising area, you need exploitation. So find, search around promising areas. And that is how swarm intelligence algorithms are dealing with these hard optimizational problems. Where, swarm intelligence algorithms by nature, they are made for continuous optimizational problems. So when the variables are real numbers. In case of hyperparameter tuning, convolutional neural network hyperparameter tuning, we have both real values like learning rate, but we also have integers as variables like number of layers or number of nodes in the layers. Or activation function, we have certain number of activation functions, we need to choose one of those. So that is not a real value, but categorical variable. So now we have mixed variable problem, and we have an algorithm that is created for continuous optimizational problems. So in order to apply swarm intelligence algorithm to the problem of optimizing convolutional neural networks, we need to adjust that algorithm for the problem. So first is, how do we adjust for categorical problems? For categorical problems, we simply numerize, which is not one of the ways to do. We numerize the categorical possible categories, and then we treat them as integers. Now, how do we treat integers? We treat integers with two possible outcomes. You have a wide range of integers. In that case, you just use the algorithm as usually and just round the solution. So if we get 2.5, we will take 3, and that is our integer. You can do that if you have large range of numbers, because you can treat them in that way. But if you have a small range of numbers, for example, number of layers, 1 or 2, 1 or 2 layers makes a huge difference in accuracy. So going from 1.49 to 1.5, changing from 1 to 2, even though for algorithm that is a change of 0.01, for accuracy is change significant. So the changes in solutions do not reflect changes in objective functions. So what we do in that case, we usually treat that as probability of getting 1 or 2, or we are using some V-shape or S-shape functions that will map that number into integer. So few examples of tuning convolutional neural networks by swarm intelligence algorithms. Again, long list of the papers, but I have chosen 3 to show because this one is the simplest, where we just adjust swarm intelligence algorithm for certain number of hyperparameters and apply to a problem where we have a data set. So it's detecting leukemia in microscopic images, blood images. So this is just to show that tuning actually works. So there was not a lot of pre-processing. We had a database. Blood cells are centered in the image. We just need to distinguish healthy versus abnormal blood cells. We fixed the architecture of the convolutional neural network, and swarm intelligence algorithm was just used for tuning hyperparameters. Sometimes we can tune search for architecture and tune hyperparameters. So these are the hyperparameters that we are searching for. So 3 in convolutional layers, 2 in fully connected layers, and general hyperparameter is learning rate. So for each of these, we have a set of upper and lower bound. So for our algorithm, how it will search. And in comparison with untuned convolutional neural networks, we have the accuracy from 96.6 to 96.7. And comparing to non-convolutional neural network approach, support vector machines, it's from 93.8 to 97.7. So this is just a first base case that shows that searching for hyperparameters by swarm intelligence algorithms can improve. So first of all, convolutional neural networks obviously improve the accuracy, and then additional tuning additionally improve the accuracy. So the second is where more focus was given on adjusting the swarm intelligence algorithm. So as it was said in the previous talk, you can go to either direction, but you can also combine. So this is a combination with a focus on swarm intelligence algorithm. So the task is to classify the glioma brain tumor grade from MRI images. And we modified Firefly algorithm specifically for that problem, for tuning convolutional neural networks for that problem. So basically, we introduced changes, adjustments in the operators, search operators in swarm intelligence algorithms to adjust specifically for the landscape of error functions, which is loss function during the training. Usually for objective functions, when we are tuning convolutional neural network, we use loss function, not the accuracy, because accuracy can vary during the training. And a little bit more details. And these are the list of the parameters. And we improved the results comparing to tuned convolutional neural network, but with the genetic algorithm. So with another nature-inspired algorithms, by specifically modifying, adjusting swarm intelligence algorithm. For that problem, we managed to improve results even more. And the last paper that was mentioned an hour ago, from 10 days ago, it's an interesting approach because it combines several different areas. So it's basically audio analysis with convolutional neural networks. But even though we start with the audio file, we convert that audio file in spectrogram, and then we have an image. So we start from audio file, but I will go back to this. We got these images. So this is the image representation of the audio file. So now these images were used as input to convolutional neural network. And this paper has several steps. First one was adjusting swarm intelligence algorithm for the problem of tuning convolutional neural network. But we didn't just use convolutional neural network from start to end. This had two layers. The first layer was to tune hyperparameters of convolutional neural network. And then when we tuned, for that we used swarm intelligence algorithm. So it had iteration of swarm intelligence algorithm population that trained through different set of hyperparameters. We see which one is better, which one is worse. So this first part is trained only through 6 iterations, because that was enough to see which combination of hyperparameters is promising and which is not. So once we train that, find the promising hyperparameters, we choose the best one for the second part, where we are optimizing a classifier. Because convolutional neural networks, convolutional pooling layers, they're basically feature extractors. So once we extract those features, we can use them as input to neural networks or to support vector machine or decision tree, random forest, to any classifier. So basically the second part is using these XBoost models that we are basically combining several of those classifiers, and we are choosing, using swarm intelligence algorithms, parameters of those classifiers. And now there is a whole list of the results that I will just go through just to see that the results are improved. But this is already online open access, so you can find details result over there. So basically, these are the CNN, in the first layer, list of hyperparameters that were tuned by modified swarm intelligence algorithm. And these are the hyperparameters of the second part, so of the choosing the best classifier hyperparameters that we used, so lower and upper bounds. And you saw this table. This is for objective function. We use that MCC, so we didn't use accuracy. This problem had really unbalanced data set. We did a data augmentation to try to balance, but in that case, if we don't have balanced data set from the start, accuracy or loss functions are not the best to use for as objective function in optimization process. But we used this MCC factor, which combines true positive, false negatives in a way to take into consideration the unbalancedness of the data set. So just to show, this is the accuracy that we got. So all these swarm intelligence algorithms were implemented in the same way and tested under same conditions. And the point is that if you modify specifically swarm intelligence algorithm for this task, you will get better results. Just to find where is the final table. I think this one. So we got, this is for multi-classification. So the first set of the tables is for binary classification, healthy lungs versus unhealthy. And this one is for multi-classification where we have 4 diseases versus healthy. So COVID, pneumonia, bronchitis, and bronchitis. And in that multi-classification we got with our modified swarm intelligence algorithm, the accuracy was 79%. While the rest was around 70% accuracy. So these are the optimal hyperparameters and more. What are the optimal values that we got for those hyperparameters? And thank you. This is how you end in half an hour.
Any questions?
Actually, it's a very, very interesting application of fine-tuning the hyperparameter of CNN using the SI, right? Swarm intelligence algorithm. But what you also mentioned at later slides that you use only the 6 iterations, right?
Yes.
But when because I understand, because for fine-tuning the hyperparameters, you formulate the problem where your deep learning model is working good, right? Mm-hmm. So for each iteration, you need to run every time the entire deep learning model, right?
No. So while you're tuning hyperparameters, you can cut in both iterations of swarm intelligence algorithm and number of epochs of training, because in order to get the objective function, you need to train the whole network. And training have several epochs.
For per iteration, how many epochs you have taken?
You have 5 epochs. So if there is somewhere a slide that shows that that with 5 you can get a good upper. So later you train it with more iterations and with more epochs. But just to get which one are promising, this is enough. So this is not for getting the final results, but for finding promising parts. So you can. We had a research. One of the graphs are showing that after 5 epochs, you can see what are the promising results. And later you can train it for 20, 50 epochs, and you will get better results. But for purposes of finding which hyperparameter combination is good, you can just use 5 to 10 epochs. And for trainings for using swarm intelligence, if you're just doing that, you will use like 50 iterations.
Swarm intelligence also you took only the 6 iterations.
In the first phase. In the first phase, because that first phase.
For tuning purpose.
Yes. Because then those results are taken in the second phase, where they are additionally tuned with the classifiers that are used.
That I understood, but if any probabilistic algorithm is giving the result in 6 iterations, then what is the use of any probabilistic algorithm? Any deterministic approach or the exhaustive search can also work?
No, because in those 6 iterations, you have the whole population of solutions.
How many?
So there was 50 in population, and you have 60 iterations. So it's not, with grid search, you're not getting that much. You cannot check all of them. And you have those 6 guided movement toward good. So this is not typical problem.
Usually what happens in swarm intelligence-based algorithm, the intelligence emerges after 100 or 500 iterations.
Yes, which happens in the second phase of training, where we have 50 iterations.
Okay.
So this is just to tip your toes to find a promising combinations with a little of guided search. And then with that and classification, you're tuning everything together using a number of iterations that will actually merge to.
And how many parameters you
It was 6, I think.
6. And have you recorded the computational time also?
Um,
Training?
No, I don't think that computational time was recorded because it was done on the server where you choose for deep learning.
It's a very interesting problem, and actually, I'm also looking for similar kind of problem. Professor Tuva also mentioned about the optimization challenges in the CNN or other related models.
Yeah, with deep learning, it's kind of weird because objective functions is very complex. So sometimes by doing more iterations will lead toward getting stuck, even though you have a good algorithm, then having a large search through several iterations and then refining with additional steps.
And Firefly algorithm you have used for this?
Sorry?
Which algorithm?
It was modified PSO, so it has elements of the genetic algorithm and ensuring diversity of population, so you can cover more search space.
Any more questions? No questions so far? Thank you, Dr. Tuva, and I would like to call Dr. Jagdish Chandran Sir, South Asian University General Chair of ICIDA, to present memento. Yes.
Thank you.
Somebody is taking photographs. Well done.
Oh, I think that we should move here
Huh?
because of the light.
We'll stop only when your father stops the camera.
Thank you.
Thank you, ma'am, for your interactive session.
Thank you. Thank you. Thank you.
Now I would like to move on to our next speaker, Dr. Nilanjan De. Currently, he is Associate Professor VT Techno International Newtown, Kolkata, and a visiting Fellow of University of Reading, UK. He has authored over 300 research articles in peer-reviewed journals and international conferences and 40 authored books. His research interests include medical imaging and machine learning. Moreover, he actively participates in program and organizing committees for prestigious international conferences, including World Conference on Smart Trends in System Security and Sustainability, International Congress on Information and Communication Technology, International Conference of Information and Communication Technology for Sustainable Development, etc. He is also the editor-in-chief of the International Journal of Ambient Computing and Intelligence, Associate Direct Editor of IEEE Transactions on Technology and Society, and series of co-editor of Springer Tracts in Nature-Inspired Computing and Data-Intensive Research from Springer Nature, and advances in ubiquitous sensing applications for healthcare from Elsevier, etc. Furthermore, he was an editorial board member, Complex and Intelligent Systems, Springer, Applied Soft Computing, Elsevier, and he is an International Journal of Information Technology, Springer, and International Journal of Information and Decision Science, etc. He is fellow of IETE and member of IEISOC, etc. Now I would like to invite him here. And for the felicitation, I would like to invite Dr. Ashit Kumar Das, Professor of IIEST Shibpur, Kolkata. Over to you, sir.
A very good afternoon to all of you. So today I am going to talk about a talk which is related to data. Because we have a conference which we mainly focusing on data analytics. Now the talk title is the bigger the better. So I think majority of you will say, okay, the bigger means it's always better. But we need to rethink this question. Why so? The first thing is, let's start from a very primitive computation which is called the decimal point computation of pi. Now people have tried to compute pi value, decimal value, and it was a record from Guinness Book record from VIT Chennai. One student of grad, he able to remember 70,000 numbers, decimal points, and it was in itself a record in 2016. But some Swedish scientists in very recent time, in 2021, I mean, they come up with a huge number computation that is 62.8 trillion numbers, 8 trillion digits. So 62.8 trillion digits, decimal points. So that is it's another record. How many days? It's 108 days and 9 hours. You can say you can imagine how many effort, how many time, and what is the power, just to prove the power of supercomputer, just to tell what that big data actually means. So now think about these numbers, 62.8 trillion numbers, and once this number computed, then people started thinking in a different way. Now to find out the circumference of Earth, we need 10 decimal points. Now to find out the circumference of Milky Galaxy, it's only required 32 decimal points. Now to find out the observable Earth surface, means universe, that is also 65 decimal points. So what is the actual, why we are computing so many numbers? So that means 62.79 trillion numbers, which is nothing but simply having no scientific value. So we are computing, we are proving our power of supercomputer. It's in itself a big data, but we need to think that whatever the data we are producing might be majority of the data having no scientific value. So this number actually tells that the bigger the better, this statement or the question need to be rethink, because these all data which we are generated might be not having any scientific value, like this case. Another example is a genome sequence. If you think about genome sequence, it's a huge sequence, but very certain part of the entire genome sequence we actually required, remaining part doesn't make any sense, even though combinatorial problem itself. Anyway, so we need to think, as I said. Now starting from the data, other point of view, if you look into the data, you will see all over, the data space, 90% of the data are never opened. That means nobody actually opened the data. Like say for example, the phone calls, the customer say feedback, the reviews, whatever these data are, nobody actually opened that data. So that data is called the dark data. So 90% of the overall data is dark data, which never actually somebody opened. So that means we don't know that the data is a good data or the big data, or it's a bad data. So nobody knows that 90% data is a good data or it's bad data. So whenever we are going for machine learning, we simply putting the data without knowing that majority of the data which is never actually opened, never tested the goodness or the badness. So that is the second thing. And all these data, that means all these non-scientific data or the dark data are nothing but digital pollution, or which you can say it's a kind of, day by day it's polluting our world, the whole globe, because all the data, whatever we are saying as a big data, majority data having no value. Now, talking about machine learning algorithms. Machine learning algorithms, the intrinsic nature is that hungriness. More and more data you are feeding, it will give you more and more better predictive result. That is a so-called thing. So the thing is, once you put garbage, automatically garbage will out. Now think about it, 90% data, dark data you are feeding, what will be the outcome? So that means we need to think whenever we are going for any predicted model, the end result all depends upon the feeded the input data. So that's why the one process is called the data cleaning process. We need to pass through any machine learning model to the first step, which is called data cleaning process. So if you fail to clean your data and simply feeding the machine learning model, the predicted model will be a failure case. That is the first thing. But unfortunately, the goodness or the badness of the data, say for example, bad data means inconsistent data, it can be erroneous data, it can be null value, it can be many redundant value, whatever. There are so many types of badness in the data.
Now, interestingly, till now, there is not a single algorithm, not a generic algorithm, which can clean the data. For all badness, for cleanness, one algorithm is there. Multiple algorithms are there. But one generic framework is not there. You have a simply cleaning process. You pass the data, it will clean the data, and it will make you a meaningful data. No. So there is a research gap till now that there is no generic framework through which if I pass my data, it will clean the data. So that is a good statement. All good data are look alike, but bad data are bad in their own way. So for each badness, we need to come up with a different algorithm. Whenever we will come up with a single algorithm, one particular generic algorithm, and we pass all those non-scientific and those bad data or dark data, and it will clean the badness, and it will make it a meaningful data, then machine learning model will be much more robust. That is the thing. So how much machine learning models demands data? That is another interesting question, because people always ask, how much data I need to feed? How much? So the how much, there is no heuristic mechanism, no optimization technique, no meta-heuristic algorithm also that actually tells you this much number of data is required for this application. So it's a kind of trial and error till that. So there is no simple algorithm which can determine, even no adaptive technique also, that this much of data you need for machine learning model. And another thing is, think about those all LLMs, so-called LLMs. As the LLMs, the development is growing on, feeding of garbage is more and more. So as you are feeding more and more non-scientific data and you are trusting on those models, ultimately you can see there might be a disaster. So deep learning model, so-called deep learning model, from 2012 onwards, once AlexNet introduced, that time onwards, it's a kind of simple memorization technique. And if you think from neural network perspective, neural network is always depends upon the main problem of neural network is it always requires variable data. If you are feeding the same type of data, system will be biased. So we need all different variable data. Now it's not about the big data. It's about big data, clean data, and variable data. So if my data is not big, clean, and variable, all those machine learning model will be a kind of disaster, a kind of biased. So that's why we need to feed our data. It's not only more data, rather more and more, this last line, big, clean, and variable data. Now another interesting part is metadata. We have many data, but we don't have metadata. If you don't have benchmark data, and that requires a lot of time. For benchmarking medical data, doctors don't have that much of time. So if you don't have comparative data or benchmark data, ground truth data, it's always difficult. But again, there are a lot of techniques, but still there is no standardized technique which can create more and more accurate metadata. So the day when the benchmark data will be created by the algorithm, we will see many of the data will be useful data, which is still not useful. So that's why there are different, one interesting area of research is to come up with lots of, you need to spend lots of money, lots of time for this, but you need to optimize these things. The benchmark data will be created by some sophisticated technique. Now, ImageNet data, talking about this data set, which is a very well-known data set. If you look into the data set, Professor Lee from Stanford University, long back in 2009, they come up with a huge data set. And all are annotated data, means labeled data. How many data? That is around 14 million data. And 80,000 distinct category. Rat, mat, hat, cat, 80,000 distinct category. Now they passes through this, there is a vision competition, every year there is a competition. Initially up to 2011, the error rate was 26%. Once deep learning introduced, in AlexNet introduced, first time, there is a sudden dip of 10%. So 10% there is a dip. And after 2015, once ResNet introduced, it is lesser than the human error rate. So human error can be there for 80,000 distinct categorization of 14 million data, but deep learning models are good enough to categorize. Now how good it is? As Professor Eva and Professor Milan was talking about these deep learning frameworks and that hyperparameter. Now look into these crazy numbers. Hilton come up with a number in 2012. They tried to categorize only 1,000, not 80,000, only 1,000 categorization. How many numbers of parameters need to tune? That number is 60 million parameters. So 60 million parameters you need to tune, and you are tuning by some certain optimization technique, heuristic or meta-heuristic, whatever, And how many numbers of intermediate nodes? 6.5 lakhs nodes. So think about it, if you are simply hybridizing two models, maybe any one CNN with some LSTM or something like that, how many numbers of parameter you need to tune? And how many numbers of, another thing is a intermediate node you need to pass through. That is huge. So without going into the complexity of the model, if you're simply going for the hybridization, might be result will be very, very good, but actually in reality, in real application, this type of all hybridization are a failure case, nothing else. So convolution neural network, people started talking from 2012 onwards, but the interesting part is, if you look into the one technique is called pooling. So if there is a 3x3 matrix, you are taking out the maximum or the mean, max pool or min pool, and you are throwing remaining all 8 pixels. Now what you are doing, you are simply discarding those pixels, but you don't know they are bad guy or good guy. You don't know what is their relationship. So neural network fails to understand the underlying relationship in between the data. So bad guy might be a good guy later. So without knowing that, we simply discard, and that is basically the fundamental flaws of CNN. And it's not actually, it's a AAAI conference where Professor Hilton itself, he himself pointed out that CNN is failure, might be failure because of this reason, because pooling is nothing but a disaster. Now, why this, talking about this AlexNet, one time we are deploying on 14 million data, another time we are deploying on 500 X-ray, 200 MR image, same network, same neural network, same deep learning framework, we are deploying on 14 million, another side we are deploying on 100 X-ray. Now think about it, getting data is more important. So we need to spend more and more gathering actual data, scientific data. Now there are some heuristic technique, weakly supervised learning, like say for example, not supervised, not unsupervised, in between this. So if you have lack of benchmark data, what you will do, you will tell our engineer that, okay, you just do benchmark for me. You are not a doctor, I understand, but this lesion need to be marked by you as an engineer. So there will be always a delta error. Now there can be one heuristic strategy also, and always consider a delta error. So in this way, might be benchmark data can be created, but again, the word suggested it's weak supervised learning. So whatever the thing is. Now talking about this, another interesting problem of machine learning, which is called small size data problem. Because once the data size is small, what to do with this data? People always talk about more and more data, big data, so many data generated, but think about it, there is a chronic disease. And on the available data is only 100. All over India, patients are 100 patients. What will happen with that data? Can I deploy machine learning models? So that is one challenge in machine learning model design. If you are dealing with very small size data, variance will be too high. And the machine will give you 100% accuracy might be. So it's a kind of overfitted case. So even though you are getting very good result, but the data availability is very less, crunch data, niche data, then what will happen? Models, whatever the results it actually come up with, those numbers are simply sloppy numbers. So that's why small size data is the biggest another challenge, where outlier is very common, and if the 50 data one outlier, 50,000 data one outlier, so always 50 data one outlier is dangerous. So that's why this small data problem is another interesting problem. And people what try to do, they always try to create more and more synthetic data. Because if you have crunch of data, you create synthetic data. I'm not talking about fake data. Fake data is different. A subset can be synthetic data. And that try is called the generative AI. What so-called generative AI. But once we started working with GAN, that time we actually did the same thing. What today we are going through this LLM and all. So we created more and more synthetic data. And now almost 60% data are synthetic. So it's a synthetic Mona Lisa, synthetic whatever, the orange, rose, whatever. Now problem is, the good part is, you don't need any privacy concern. There is nothing. You don't need any permission. You simply take and create any MRI data. You can access that data. So there is no patient privacy. There is no kind of, consent you need required, because it's all synthetic data. So that is good part. But the bad part is, we don't know where to stop. Because 60% data is now synthetic. Might be someday there will be 90% data will be synthetic. Then it will be a kind of another case, maybe you actually fail to identify how good the data is, means how actual real is, where to stop. Now talking about very primitive technique back, say one technique is called the data augmentation technique. So if you go for zooming, zoom out, stretch it, straight out, So many people works in this particular area. They increase their data volume 10 folds, 20 folds, 30 folds, paper got published. But if you look into all these techniques, say for example, elastic deformation, changing the variance level, contrast level, you create many images. So from one images, you create many images. These are called geometric transformation. These are very popular. Even random cropping, maybe the foreground and the background, which is called the alpha blending technique. Old days in TV, there was alpha tuner. So similar kind of thing. So there will be an alpha, background, foreground. You change many images you can create. Or maybe that you change the variance level of the kernel and you can create many images from one particular images. But think about it, you are creating all those images from a base image, fundamental image, one particular image. That means it's nothing but redundant data. So that means data augmentation technique, even though it's good enough to create many folds images, it can create 100 data, 1000, but ultimately all those 900 data, additional data, it's a propagation of the same type of noise, nothing else. So again, these techniques fails. Now, another thing is, if you think another one step ahead, the transfer learning model. Transfer learning model means you are solving a particular problem domain where you have lot of data and you are trying to solve a problem where the data size is very small. So you try to solve that problem in the large space. Whatever the knowledge you gathered, you need to transfer these as a frozen knowledge to solve a problem where data is a crunch data. Now what happens exactly there? If you talk about this huge data set means, say for example, ImageNet data, which is a huge data, and you have 50 MR image, you are trying to solve a problem on 50 MR, you failed, you transfer that frozen knowledge from the large space. What happened? The ImageNet data, if you look into the data, you will see all the chairs are very good looking chairs. They are taken from a proper lighting condition, proper brightness, proper shape, proper angle, all are so-called good data. That means all those ImageNet 14 million data are so-called good guys. There is no bad guy. Now if you train your system with all those good guys and you transfer that knowledge, that all are good knowledge you are transferring. But it failed to capture the actual chairs in reality, or maybe the data are messy. So that's why this is another failure of huge data. It's a fundamental flaws because ImageNet data itself having this issue. It's all taken good data, not bad data. Now how robust these all deep learning models are? People say these are enough robust. One particular scientist, the group, they come up with a very interesting paper in TC. They have shown if you remove one pixel, one single pixel, a cat can be a dog or a dog can be a cat. So that means what I'm saying is one pixel can make the difference. So that's why this is a nice statement. Deep learning models are quite good enough for many cases, but still not foolproof. Now talking about few more slides, 3-4 slides, talking about the explainable AI. People always talk about explainable AI. So there is a performance and explainability of the model. You need to grow the trust of the model. Now what happened if you talk about the naive Bayes, if you talk about the support vector machine, random forest, gradually move into deep framework. What happened? The performance is getting improved, but accordingly we'll see the explainability getting is lesser and lesser. Now we need to there is a trade-off. So I need a model which can be interpretable, which can be, you can say you can interpret that model, translate that model, whatever. But the problem of this, if you look into this model, the last point is very important. XAI models, all XAI algorithms, if you look into SAP, if you look into any global kind of thing, maybe any other SP Lime or Lime, whatever, you will see it always behaves for the AI model. It always talks about the AI model, but it never talks about the training data set. Explainable models only explains the behavior of the model, never talks about the data. So even though explainable AI is good enough to explain, so that's why there is another question. Why should I trust explainable AI model? The previous question, why should I trust your model? Now the question is the way you are explaining, that need to be trustable also. Because the models need to be explainable, that's fine. But the training data also need to be explainable. But XAI having this limitation. If you go through the second point, you will see the correlation might be exactly same. But in reality, output may be same. But in reality, it doesn't work, which is another causality problem, issue of this explainable model. So these are few of the model bias and the data quality matters. Lastly, LLMs are good enough, but think in a way, if you are driving 6 kilometers and maybe using a CNN of 6 layers, maybe they are actually emitting same amount of carbon. So once we are talking about the sustainability, once we are talking about this energy emission, we need to think how good these deep learning models are, not from complexity point of view, not from space or time. We need to find out the complexity of the carbon emission. So that need to be identified also. Lastly, human you can't avoid. Even from industry 4 to 5, if you move, again human intervention is there. So human in a loop might be a better future for machine learning. I'm not sure. And another thing is how real that is good enough, where to stop. The synthetic data generation is fine, but we need to find out, okay, I should stop and will not create more and more synthetic data. And lastly, the last point is we need to find out different other techniques also for machine unlearning, because unlearning is very important. If you train your data with some data and you are getting a trained model, now after 10 years, somebody claims that I need to dig out, I need to roll back, revoke my data. So we need to go for retraining the whole model, or I have a model where I only put that trained data and I can simply discard that data and the model will work as it is. So that is because there are a lot of data privacy issues, and maybe people are trying to find out their own data and they're taking back those data. If these things happen, all those trained models, you need not have that much of money to retrain, or you can't spend that much of time for this. So we need machine unlearning models also. So people need to think about unlearning. Thank you very much.
Thank you, sir. Any
Thank you.
questions? No questions so far. I would like to invite.
Okay.
I would like to invite Dr. Abhishek Bhattacharya. Oh, I think you have a question, sir.
No, not question, but actually I really appreciate this concept of machine unlearning, and it is actually very, very much required. But just imagine a situation that I existed on Earth, right? I died, and before that, my wish is that my all records would be removed from this. Then ultimately, I'm vanishing the knowledge base of the system, and
that is what I'm saying, sir. Suppose
then the
in
machine
social
will not
media,
be as intelligent as it was.
it needs to be there. When suppose, say for example, in social networking site, 1,000 people died today. Now those data need to be removed. That if based on that, if there is any recommendation system is running. Now I can't, retrain the whole model because it's already trained. Now if I take out all those 1,000 data, the model will react and work as it is. So there needs to be a kind of data-driven, knowledge-based system which actually, filled up that 1,000 data.
No, but that 1,000 data means records, removal of the records is okay. Recommendation system removal is okay. But like when they were on the social media, there were certain habits. They have some background. Based on that, there are some that okay, from this India background, they buy this, they do the friendship like this, they comment at this particular time, they attend these kind of seminars or something. This kind of trade should be utilized for the future generations. This kind of learning should not be removed from the algorithms.
That's fine. Sir, what I'm saying is, see, if somebody is not claiming his own data, it will keep it as it is. But if somebody say that, okay, I don't need my personal data, I need to revoke the data. So what will happen? So you need, see, in databases, we never delete the data, generally. There is a deletion flag, 1, 0. So you simply change that flag from 0 to 1 or 1 to 0. So maybe the data will be there as it is, but there will be a flag kind of thing or something, one strategy, which can actually make it active, not active. But once it is not activated, whole model should not get affected. So how to minimize these things so that the model need not to be retrained. So the objective is minimize. It's a kind of optimization problem also. So I need to come up with some optimization technique.
It's another kind of training.
It's another kind of training, but it's not retrained. So it will not take exactly the same amount of time, same money, but somehow I need to manage my data in such a way that the data will go out from my system, but it will not hamper the whole training model.
Any algorithm available?
It's already there, sir. There are very few groups who are working last 2-3 years, but now because of this, India having their data privacy law, Australia having their, Canada having their, and European country having their own data privacy law. And lot of people are actually claiming
India will also come.
I started with, I give my data for machine learning model. Now after 10 years, I've gone through that only 1,000 patients are there in India. Now I think no, it's my own data, I should not share, so I need to take my data back. Now in this kind of scenario, it's very important to go for, because of the privacy concern.
No, as such, just for your information, India is also working very hard
For this privacy, data privacy.
for the privacy rules and
So already
policies.
first
policy
draft is already
Yeah, drafted.
created. It seems
It
to
will
be.
come.
I forgot the name. Maybe start with G or that. There's policy. I mean, it's already fixed for the policy.
You know that one that Mukesh from the Jaipur, he joined at NIC.
NIC they are part of this whole thing.
Yes. So he's the in charge of that. Mukesh. He was earlier in the Jaipur.
Okay.
I just forgot the
Yeah.
surname.
So this right to forget. So this thing should be implemented.
For the statement, the next stop can be the title with forgetfulness is a good. Forgetfulness is good thing. Means
Actually.
as much as you forget, it's good to go for another round of training. So it's not learn, unlearn, relearn. It might be not relearn, we skip relearn, but learn and unlearn should be always there. Because only machine is getting trained and trained and trained, there will be an overtrained. And if machine thinks, there will be an overthink also. So in machine learning, there is an overtrain also. There is a drop down or something. There are different techniques by which we can the dememorization. There is a technique of dememorization. So we always try to memorize, but there is a time we need to dememorize also. So it's a kind of similar kind of thing. But it's a very less people are working in this area.
Holiday time for machines.
Quality time for machines.
Thank you, sir. So, please, sir, Niranjan sir, please be here. I would like to invite Dr. Surajit Gun to felicitate Dr. Niranjan Dey.
Thank you, sir. Thank you very much. Thank you.
Thank you, sir, for the session.
Thank you.
Next, I'm delighted to introduce our last keynote speaker, Professor Shenglang Peng, a distinguished professor and a director of the Department of Creative Technologies and Product Design at National Taipei University of Business, Taiwan. Professor Peng holds a BS degree in mathematics from National Tsinghua University and an MS and PhD in computer science from National Changchun University and National Tsinghua University, Taiwan. He is an honorary professor at Beijing Information Science and Technology University, China, and a visiting professor at Ningxia Institute of Science and Technology, China. Additionally, Professor Peng serves as an adjunct professor at Mysore University and Kazi Nazrul University, India. Professor Peng plays an active role in the academic community, serving as an Secretary General of the ICPC Contest Council for Taiwan and the regional director of ICPC Asia Taiwan site. He is also a director at the Institute of Information and Computing Machinery and Taiwan Association of Cloud Computing. His extensive contributions include reviewing for top journals like IEEE Access, IEEE or ACEM transactions on networking, and many others. His research focuses on the design and analysis of algorithms, particularly in bioinformatics, data mining, and networking. Now, I would like to invite Dr. Surajit Gun, convener of ICIDA 2024 and academic director of eminent group of colleges, to be here. I think he is missing right now. I would invite Dr. Saurav Majumdar sir, the professor of eminent College of Management and Technology, to be present here and felicitate Dr. Peng. Sir, photo. Thank you. Over to you, sir.
So, where's my slide?
Your slide.
Yeah. I give the appreciate. Maybe you put the. Is it here? I don't know which one. Can you ask appreciate where? Maybe I can find my USB. Yeah. Do you have? Yeah, I think we have. এতে রাখছি ডেস্কটপে ডাউন করে This for the and the talk here. This one? Yeah. No. Yes. Like so. Yeah, so. Maybe I can stand here, okay?
No problem.
Here, okay. Okay,
You don't mind standing here?
I stand here.
No problem, right?
Okay. Thank you very much for the introduction. I'm Shen Longpeng, come from Taiwan. Actually, this talk will be very different from the others. It's a part of my research project. It was end on this October. Yeah. But anyway, it's just for theoretical interest. I think I'm very happy to be the last one, so I can shorten some technical part. Okay. And yeah. Okay. The problem is work on graph. I think a graph is a very popular data structure, and it can formalize many problems. Okay. So at first, I would like to introduce some traditional problems. The first problem is called a domination problem. In the problem, we want to find a subset and then can dominate the others. Okay. Of course, the objective is to find the dominant set as small as possible. Let me show you an example. What is a domination? Okay, if we choose the yellow one vertex, okay, then we can dominate its neighbors, okay, like you can see the graph here. And then if we choose this one, so you can check every vertex can be dominated by these two vertices, okay. Another problem called the vertex cover problem. It is also a very traditional problem. You can find it in Richard Kopp's paper. In this paper, we want to find a vertex subset to cover every edge. Okay, so if we choose let one in the we can cover those brown edges. Then maybe we can choose these two vertices. However, we cannot cover the the remaining edges. Okay, so next one we maybe choose this one. Okay, and then this one, and then this one. Okay, it is not enough. Okay, then this one, finally this one. So you can check. We need a lot of vertex to cover the whole edges. Actually, for each edge, we need one end vertex in the cover set. So actually, it a little bit like this is an edge version of a domination problem. Okay, because in domination problem we want to dominate vertices. Okay, and for this vertex cover problem we want to cover all the remaining the edges. Okay, so it is very easy to generalize to the K domination. Actually, it is a little bit like fault tolerance. Okay, so for the K domination problem, we need to find a dominant set to cover the remaining vertex, and each remaining vertex can be dominated by at least K vertices. So for example here, if we let K equal to 2, so we can choose this yellow vertex as a solution, a part of solution. Then it can dominate its neighbors. Then this one, okay. Then you can see some vertex can be dominated by 2 vertices. So actually, it's a little bit the color is very different. Okay, like this one is gray. Okay, but anyway, in this screen is not gray. Okay, anyway, when we choose these 4 vertices, we can check every remaining vertex can be dominated by 2 vertices. Okay, so this is a 2 domination problem. So actually, this problem we can show it is NP hard. This is a polynomial time reduction. I think I have to go faster. Okay.
So the remote is there.
Oh, yeah, it will be better.
You can come in.
Here is okay. Okay. So anyway, this reduction shows that the K domination problem is NP complete on split graph. Theoretically, if a problem is NP complete, means it is very hard. Okay. So now we see a well-known domination problem with propagation property. Actually, if a problem with propagation property, it becomes harder. Okay. A problem called a power domination. Okay. In the power domination, okay, similar to the domination. However, we can see here is domination. Use the domination rule. Initially, for all vertices in the closed neighborhood S are dominated. S we assume that S is the power domination set. Okay. So now, what is the propagation in the problem? Okay. For a dominated vertex U, if only one vertex V in its neighborhood, okay, then which is undominated, then V is dominated. So this called the propagation property. Let me show you an example here. For this graph, if we choose this vertex as a solution, then its neighbor is dominated, okay? Then only this one, because only one undominated neighbor, so this is propagation, okay? And then this is dominated, then this one, or you can check this one, I think for here, then use this here. You use the propagation property, so the domination power can propagate to this vertex. Then here, okay, so for this graph, only one vertex is enough for power domination, okay? Yeah, this is a solution, okay? So what is the difference between dominating set and the power dominating set, okay? You can see for this graph, two vertices are enough for dominate the whole graph, okay? However, for the power dominating set, if we choose this one here, then use the propagation property here and then here. So one vertex, this one, only this one is okay for the power dominating set problem, okay? So yes, this reduction show later the power dominating set is very hard. I think I can skip this example, okay? Also, we can do a reduction from the vertex cover problem. But anyway, if you like this mathematical reduction, okay, you can refer my slides, okay? So another view for the power domination, okay? Because we just mentioned later that vertex cover problem is an edge version of the domination problem. So we can see just check the edge, okay? So, so here, observation is for the edge. At first, all edge in the, if S is the power dominating set, so all edge in the induced subgraph of here, okay, are observed, and all vertices in this set are reachable, okay. Implication means that for two reachable vertices U and V, the edge between lane is observed, okay. So the propagation means for reachable vertex U, if UV is the only instant edge of U, that is unobserved, then UV is observed, and V becomes reachable. Okay. So it's a kind of vertex cover with propagation. Okay. So actually, in the power domination history, somebody said it's come from the Kirchhoff current law. Okay, it means, okay, for a junction, okay, the input current should be equal to the output. Okay, so it means if we use the domination language, we can some dominant here, then can propagate to the remaining vertex. Okay. So this problem can be generalized to K power domination. If K equal to 1 here, okay, if you choose this vertex as a set, as a solution, because they cannot propagate because they have two undominated observate edges, okay? However, for k equal to 2, yes, by the propagation property, they can propagate to its neighbor. Okay, so now we go to another graph problem with propagation property. It's also a very famous problem in data mining called inference maximization problem. In this problem, we are given a social network and a diffusion model and a positive integer k. The inference maximization problem is to find a vertex subset S such that its size is equal to k and the inference is the maxima, okay? Initially, all vertices in the C set S are inferenced. Then, according to the propagation rule, we want to maximize the f of S, okay? The idea like this one in the social network, okay? If we choose some very powerful men, powerful people, then they try to influence their neighbors, and we want to make the influence as large as possible. Okay. So actually, there are many models for this problem. I introduced two basic ones. Okay. The first one called the linear social model. In this model means if you will be influenced, your neighbor, the probability to influence you, the summation is large enough. Okay, so here means here if it is satisfied, maybe this is a personal property. Okay, then you will be influenced. Okay. Another one called independent cascade model. In this model means in your influence neighbor, if only one, if it is powerful, then you will be influenced. Okay, you will be okay. So of course, this problem can be generalized to the K inference, also called the min-max problem. But anyway, in the following, I will assume there are no diffusion model. Okay, in order to combine the power domination problem. Okay. In this problem, initially all vertices in S, the C set are influenced. Then, if it can be influenced, if there are k neighbors, okay, enough to influence vertex V. Okay, so of course this problem is to want to maximize the influence number of members in the set. So, okay, this is called, if we want to influence the whole social network, so we want to minimize the K, okay? If our budget is limited, we can only provide K%. Then we want to maximize its impact, okay? So let me show you two examples. If K equal to D equal to 2, if you choose these two vertices as a solution, okay, then we can check how many people they can influence, okay? For example, here, and here. So, and then by propagation rule here, and then here, totally you can see the number of influence vertices are 6. However, if you choose these two, okay, Then by the rules of this K-inference maximization problem, okay. Then here, and by propagation rule to there, okay, here and then here. So finally, if you choose these two vertices as a solution, the whole graph can be inferenced, okay? Okay, actually, we can show this. For k equal to 1, this problem is very easy on an iterative graph. Because in breadth first search or depth first search can inference the whole graph. However, for a directed graph, this reduction show rate, this problem is very hard. Okay, this is shown by the set cover problem. Okay, it means in this directed graph, if we can find these three set, we can cover this element. Okay, then we can solve the one inference problem. Okay, but anyway, it's a little bit hard. So I think this problem is NP complete if k equal to 1. Okay, this is okay. Then W inference means because every one is different. Okay, so use a function W of V to control how it will be inferenced. Okay. If WV, AVV, WV equal to is degree minus 1, then this problem comes to the power domination. Okay. Okay. Anyway, so yeah, I have to go to here. For the minimization, the maximization, for the power domination problem, we want to minimize the dominated set to dominate the whole graph. For the inference maximization problem, we have only k member in the C set. We want to ask them to inference as many people as possible. Okay. So for the inference maximization problem, in the initialization is the C set, but for the power domination is the close neighborhood of S. The propagation rule used in the inference maximization is called inward load, but for the power domination is outward load. And in the inference maximization, we want to maximize f of s, and for the power domination, we want to minimize the number of cardinality in S. Okay, this problem usually proposed in the data mining. This problem is a very traditional combinatorial problem. So how to combine these two? You can see this AV called inference neighbor, and BV calls an inference neighbor. Okay. So if we compare AV and BV, actually AV is to determine whether V can be inferenced or not. Actually, we can consider these two factors. AV is the factor that V can be inferenced, and the BV is the factor that V's inference can be propagated. Okay. For the majority inference maximization problem, it means in your neighborhood who are inferenced, the number of inferenced neighborhood is at least a half of the degree. So we can say something about this related problem. In the power domination, we can generalize into the K power domination. for the inference maximization, we can generalize to the K inference maximization. Later, K inference maximization can be generalized to the W inference maximization. Then for the majority inference maximization, they consider both the power domination rule and the inference maximization rule. Okay, so actually, if we consider the factors AV and BV, you can see BV is equal to 1 for power domination, and the BV is at most K for the K power domination. For the K inference maximization, AV is at least K. For the W inference maximization, AV is at least WV. We can define this function according to everyone, okay? So for the majority inference maximization, AV should be greater than BV, okay? Of course, we can consider another issues in this problem, okay? For example, the propagation speed, okay? Sometimes maybe, for example, the COVID-19, I think that the propagation speed should be very fast. Okay, maybe it's like the one inference maximization problem. Okay. Okay, thank you very much for your attention. Okay, please enjoy this conference. I think I have no time to ask the question. If you have any question, you can write to the email to me. Okay, thank you very much.
Any questions?
We will send the email.
I would request Professor Bilantuba to come here and present Professor Zhang with memento. Thank you, sir. On behalf of the organizing committee of ICIDA 2024, I would like to express my heartfelt gratitude to all our esteemed speakers and guests for their invaluable contributions to the success of this conference, Day 1. Your insights, enthusiasm, and collaborative spirit have not only enriched this event, but also have fostered an environment of innovation. We are truly honored and grateful to have you as a part of this remarkable experience. Without much ado, I would like to invite Dr. Milan Ivatuba here to honor our students. I would request all the students, Jahira Pavin, Shaheli Shaha, Tornov Datto, Shivam Shadhukan, Shona Khajra, Thank you, everyone. Thank you, ma'am. We will now take a short tree break before proceeding to our technical sessions. After the break, we will continue with our 2-track. I kindly request the participants to be present.